One of the main ways that we will estimate our complex line integrals is by using arc length line integrals. And it seems like I've spelled integral wrong here. Integrals, integrals. Okay. So these will be written, well, in a calculus class, they're usually written as ds, but we'll usually write them with absolute value dz, and that notation will be very good for us. But it'll be an integral over a curve of a function with respect to the element of arc length is how old books say it. So a small change in arc length instead of a small change in z. But luckily this is defined very similarly to our line integrals. We replace our approximating sums, which will have this same notation. So I'll have a times the arc length element, an approximating sum for it. We'll use, again, a partition of the interval on which the curve is defined and a tagging, and we get sample points and all that stuff just as we did before. And an approximating sum will look like this. So I'll evaluate A at a sample point and I'll multiply by the change, by the absolute value of the change in Z. So these will be our approximating sums. And then you'll say that the arc length line integral exists if these approximating sums approach a specific value that's invariant under, well, that doesn't change too much when you refine the partitions. So it matches the earlier definition of when a line integral exists. I'm not going to rewrite it all because you just have to change approximating sums to this. But we do get some nice things out of that complicated definition. It's clear to see from the approximating sums now that if I integrate over the reverse of a curve, an arc length line integral, it doesn't change anything. So it's the same as the original one, versus a line integral depends on the direction that you went. So integral over minus gamma will equal the negative, the integral over gamma. But arc length line integrals, because we have this absolute value here, don't change when you change the direction. And you use arc length line integrals to define the length of curves. So the length of a curve will just be defined as the arc length line integral that you get by replacing a with just the one function. And one thing nice about this is you can even define this length in situations where your approximating sums are tending to infinity in a certain sense. So you could interpret this as a supremum over partitions and taggings of approximating sums, because by the triangle inequality, so if I have a delta z, so maybe I'm computing, delta z2's absolute value somewhere, and I refine my partition by putting a point in between z1 and z2, well, so then my next approximation will have some point in between. And you see that by refining the partition, you only get bigger and bigger stuff. So this length can be computed as a supremum over all these. And so you can even just declare that the length in all cases is equal to the supremum. And then sometimes you just get infinity. If the length is finite, you call the curve rectifiable. But in any case, you can still define it for any continuous curve. It could be infinite, though. Also, what you get straight from our approximating sums is that the absolute value of the line integral of a over gamma can be bounded by the arc length line integral of absolute value of a And you can even bound this by the maximum of A over the curve times the length. So this first bound comes from just looking at approximating sums. So here would be an approximating sum for the line integral, and we would just be bounding it by an approximating sum for the arc length integral here. And then you can bound these by the maximum of A, and then you'll just be left with a bunch of absolute values of delta z's, which would give you the length. We also have from our definition that our arc length line integrals are independent of the parameterization of gamma, because it just depends on the points that we're picking. And we have a proposition similar to for line integrals, that if I have a piecewise C1 curve gamma and a continuous function, then the arc length line integral of A modulus of dz exists and is equal to something similar to before. I just put gamma into A and replace absolute value dz with gamma prime of t dt, and the proof of this is very similar to the one for line integrals, which I just sketched it a little bit earlier, but you'd have to modify it slightly, but it's nothing that we want to dwell on, but I'm happy to talk about it if people are interested. Okay, and so we can finally use this to compute the length of a circle. It seems like this should be more fundamental, but we really sort of created pi out of properties of the exponential function, used the exponential function to parameterize the circle, and now that we have this notion of length, we can show that the length of the circle of radius r is what it's supposed to be. So the length of the circle of radius r, we compute using the previous proposition. So we'll just do, well, it's supposed to be this dz, but then I put in my parameterization. Here's gamma prime of t, and I put absolute values on it and integrate dt, but e to the it as modulus 1, so does I, so I'm just left with r, and I'm integrating from 0 to 2 pi to get 2 pi r like I'm supposed to. Okay, let's look back at the example from the last slide. Here's this polynomial again, 1 plus z squared plus z cubed. And earlier I posed the question, oh, can we estimate p to the n dz in modulus? And we can by the earlier estimates. So this is less than or equal to the modulus of p to the n using an arc length integral. And so I could bound this by the maximum of p on the line segment to the nth power times the length of the interval is, or the length of the line segment is just 2. And then if you wanted to really estimate this, you'd have to find the maximum of p on this line segment. And I went through that by just putting it into p and seeing where it had a maximum. And it's maximized when t equals 0. You can check for yourself, but I don't want to explain all the algebra. So the maximum occurs at t equals 0. And so we get the maximum as 1. And so we get this estimate for these powers. We get this bounded by 2 independent of n. And the question is, can we do any better? And the answer is yes, we can do much better. And here's why. Well, p to the n is a polynomial. So to compute this, we just have to find an antiderivative and evaluate it at minus I and I. And to estimate it, I have to be able to bound it on this certain curve. But I don't have to follow the original line segment. This integral here would give me the same thing if I followed a different path. So look over here. This is a plot of the level curves of the modulus of P. And so here we have zeros at minus I, and minus 1. And we're integrating along this curve here. And the real significance of that curve is in the estimate, because in computing the integral here, I just evaluate an antiderivative at 2 different points. But we can get better estimates by picking better curves. So here's a better curve to pick. When I follow, well, here, the original curve is bad because I sort of cross this level curve here, and I'm picking values bigger than they need to be all along this stretch. And so that'll get reflected in this arc length integral here. So these are all bad choices right here. What's smarter is actually to head towards this crossing point here. And this is called a saddle point. And if you head here, I haven't crossed into these higher values of modulus of P here. And now, well, you could sort of follow along this level curve, but it sort of bends to the right. And so just by kind of eyeballing it, you could check this more precisely, but you might as well follow sort of as short a curve as you can to improve your estimate. And so by doing this, I'm making my curve short, and I'm choosing places where the modulus of P is small. And then I'll head to the final point just along a straight line. And this actually gives us a much better estimate. So it won't change, the curve doesn't change the value of this integral, but it will change our estimate here. So if I do so as I said, P to the n has a global antiderivative, so we can choose a different path from minus I to I to get a better estimate. And this new path, so it actually goes from minus I to the zeros of the derivative of P. We don't need to go into those details right now, but that turns out to be why those are saddle points. And so if you follow the curve here and here, you get that the maximum of P along this new curve is the value at these derivatives, which turns out to be like 0.77. And then the length of our new curve is a little longer, it's like 2.2, but we get a much better estimate now. So our original integral, I can bound it by the length of our new curve times the maximum of P on the new curve, which is now 0.77, but I have P to the n, so I get this to the nth power. And so now, where before I had bounded by just by a constant, now I actually get exponential decay. So this shows much more what's happening. So I hope this illustrated some of the ideas of these curves. So this is very fundamental, sort of basic stuff, but it has to kind of be laid out carefully for us to get to the important theorems that we can now prove for holomorphic functions related to complex line integrals.